All right, so chapter 7 is about work and energy. Okay. You guys know the principle of conservation of energy, which states that you cannot create or destroy energy. Okay. So, from an energy perspective, everything that you do in life is transferring energy from one object to another. And in the process, you probably are also transforming the type of energy. So, for instance, when I lift this object up, what I've done is I've transferred some of the energy from me. I used up some of the energy that was in my body and transferred it to this object, converted it into potential energy. Okay, so I transferred energy from me to this object. I also transformed it from chemical energy to mechanical energy. Okay. So how do you transfer energy from one object to another? You do that by doing work. Okay. And so that's why we're talking about these two topics together. So one of the mechanisms of transferring energy is by doing work. Okay. Now, to do work, you need energy. So here's another way to look at it. To do work, you need energy. And then you're transferring this energy from here to there. Okay. So we'll talk about, so those two things are related. We'll talk about kinetic energy first, work, how to calculate work done when you apply force on an object. We'll talk about the work kinetic energy theorem and so on. Okay. So energy can be transferred to an object by doing work on the object. Okay. So one way of transferring energy to an object is by doing work on the object. So for instance, this fella is pushing this cart or this lawnmower, and when this lawnmower moves, he's doing work on the object and he's transferring energy from him to the lawnmower. So if you do 100 joules of work on an object, 100 joules of energy is transferred to the object. Okay, so if you do 100 joules of work on this object, you've transferred 100 joules of energy to that object. Okay. Now, generally, when we do work, when a person does work, we are about 20% efficient. Okay, so what does that mean? You used 100 joules of energy to do work. You ended up doing 20 joules of work on this object. I'm talking about a person. So what happened to the other 80 joules of energy? It was lost as heat. Okay, so it wasn't, it didn't get used as intended, but that's how efficient you are. Okay, you are not destroying energy. It might just not end up where you wanted it to end up. Okay. So to do work, one needs energy. All right, so a lot of the work, a country can't be rich unless it has a reliable source of energy. Okay, so we'll discuss where the world gets its energy from and the consequences of our choices. Do you know what does most of the work in the world? Who does most of the work in the world? Electric motors. Okay, so we'll look at that. All right. Energy is a scalar quantity. Okay. Associated with the state of the system. Okay, so what that means is if you have a system, it doesn't matter how it got here. The energy content of the system just depends on the state of the system. Okay? So the gas in this room has a certain amount of energy, and it doesn't matter. The history of this gas doesn't matter for how much energy it has. Okay? Energy cannot be created or destroyed. Again, so the total energy of the universe is conserved as far as we know. Okay? So this picture has a lot of information. We said energy can only be transferred from one object to another and transformed from one form to another. So most of the devices that we use in our lives are energy transformers. Okay, so let's look at what that means. Okay, so let's look at some of the devices that you use. So what does a light bulb do? It converts electrical energy to electromagnetic energy. That's what that device is doing. Yeah. What does an electric motor do? It converts electrical energy to mechanical energy. So an electric vehicle is that. Okay. What does an electric generator do? Again, generator is a bad word. It should be electric transformer. What does an electric generator do? It converts mechanical energy to electrical energy. Yeah. Can you give me an example of this? Where do you see this?
Like a steam engine.
Steam.
Those things that use water to turn into electricity.
So in a dam, the energy of the water is converted to electrical energy. In a windmill, the energy of the wind is converted to that, and so on. Chemical energy, via oxidation, you can convert that to electromagnetic energy. Photosynthesis is the process by which electromagnetic energy is converted to electrical energy. This is what the plants do. Phytoplanktons are what harness all our energy from the sun, I guess. So. Nuclear energy can be converted to radiant energy. You guys know where this happens? It happens in the sun. Okay. So let's briefly talk about that. So in the sun, what does the sun do?
Reacts hydrogen or helium will not react, but it uses the heavier element to raise the temperature.
Right. So in the center of the sun, the temperature is 15.6 times million degree Kelvin. Okay, so like our friend said, what the sun does is the following. It takes 4 protons, that is, these are hydrogen nuclei, and squeezes them together. I'm not going to give you all the details, just a little bit. All right, so we'll look at what's happening. So here are 4 protons, okay? And at the center of the sun, what happens is they're brought together and converted into a helium nucleus. And then you get energy. Okay, why do you get energy in this process? Okay, for you to get energy, the products has to weigh less than the ingredients. Okay, so the mass, anytime you have energy, the mass of the product has to be less than the mass of the ingredients. Okay, why does this guy weigh less? By the way, so in this process, again, we are not going to worry about the details. You see that 2 of the protons got converted to 2 neutrons. They emit a positron and stuff like that. Okay, so they emit a positron and a neutrino, and right now trillions of those neutrinos are passing through your body every second. Okay, as a result of that, and they're doing you no harm. But anyway, so why does this guy weigh less? Okay, so I'll give you another example. Okay, so let's say you go to a store and buy a proton and an electron, and we'll just play numbers. Okay, so this fellow is about 2,000 times heavier than this guy. So let's say this guy weighs 1 unit, this guy weighs 2,000 units. And then you're bored, and so you put together a hydrogen atom. Okay. How much does this guy weigh?
2001.
2001. Good. You got it. So this guy weighs less than 2001. All right. Anytime you form a bound state, okay, so whenever things attract and you form a bound state, that product weighs less. Okay. So how much less does this weigh? Do you guys know what is the ionization energy of the hydrogen atom? No? All right. So now you know, and you're going to remember this forever. 13.6 electron volts. Okay, so it takes 13.6 electron volts to ionize hydrogen. And that's how much less this guy weighs. Okay? So now we understand if you form a bound state, an object weighs less from the ingredient. What do you think will happen if you form a stronger bound state?
It'll get lighter.
Very good. The stronger it's bound, the less it weighs. Okay? So you see, this guy, this is a bound state, and it's bound by the strong force, which is much stronger than this guy, this force, okay? The electromagnetic force. So this guy weighs less. And you guys have seen Einstein's equation, mc squared? Okay. So how much ever he weighs less by, this guy, all that converted to energy. Okay? So in the sun, if this guy weighs 140 units, this guy weighs 139 units. Okay, so roughly 1% of the mass in each reaction is converted to energy in the fusion reaction. Okay. And this energy is released as gamma radiation and stuff like that, mostly. Okay. And that's what this, so there is an example of nuclear energy being converted to radiant energy. In a fusion reaction, we do the opposite. In a laser-induced fusion, the input energy is laser energy, and then we get nuclear energy. Okay. So where were we? Okay. So in the sun, and so here's another point. Now these guys are positive charges. Okay. So these positive charges, if you shoot two protons at each other, what happens? They repel each other, so they'll fly apart. You shoot them faster, they'll get closer, and then they'll repel each other. For you to make this bound state, you need to come within 10 to the minus 15 meters, 1 femtometers. Okay, if you come that close, then the strong force, which is 100 times stronger than the electromagnetic force, that takes over and forms the bound state. Okay, so that's why all nuclei are about this size. You have to be that close for the strong force to overcome the repulsive electromagnetic force. This strong force is 100 times stronger than the electromagnetic force. Except that the strong force works at a range of 10 to the minus 15 meters. Okay, so to bring those protons that close, you gotta have it very hot, so they're moving very fast and they'll come close together. All right. Now, I was telling you all this just because I wanted to bring home the fact that this picture contains a lot of information. It shows you all devices that we employ in our lives. Okay. So a battery converts chemical energy to electrical energy and so on. Yeah. So here is a form of energy that you're familiar with. Kinetic energy is the energy contained in a moving object. So the energy contained in a moving object is 1/2 mv squared. V is the speed, m is the mass. Okay, we'll define something called linear momentum. Linear momentum is a vector. Okay, so it's mass times velocity, and the linear momentum square. So kinetic energy can also be written as the linear momentum square divided by twice the mass of the object. Okay. All right, so now we'll show you how to calculate how much work you've done when you apply a force on an object. Okay. So let's say this guy is pushing this lawnmower. There is the force applied, and this is the displacement of the lawnmower. Okay. As long as he is applying, this force is constant throughout the motion of the lawnmower. If this force is constant, the work he's done is this dot product. The dot product of the force and the displacement vector. In this diagram it's D, but here I've written as S. Okay, so here's an object. Let's say you apply a force like that, and the force is constant throughout the displacement. Then the work you've done is force dotted with the displacement vector. Okay. All right, so this is assuming a straight line motion. Okay. So, and you've seen that the dot product is defined as the magnitude of the force times the magnitude of the displacement times cosine of the angle between them. Okay. Now, F cosine phi is the component of the force along the displacement. So this is Fx, if you want. Okay, so the work done by a force is the component of the force along the displacement times the displacement. Okay. All right, the units of work are forces are measured in newtons. This is in meters. What are the units for cosine phi? They're dimensionless. This is dimensionless quantity. Okay, so it's Newton meter. Newton meter are the units for work done, and this is called a joule, after Mr. Joule. All right. So when you do a certain amount of when you do 100 joules of work, what you have done is transferred 100 joules from you to there. Okay, work and energy have the same units. Okay. So work and energy are scalars, and their units are joules. Now let's look at this formula. So let's say you apply a force on an object. If S is 0, how much work is done? I'm sorry? Nothing. So if S is 0, work done is 0. What about if phi is 90 degrees, if this angle is 90 degrees? What is cosine 90? 0. So if the force is perpendicular to the displacement, that force does no work. What about if this angle is an obtuse angle? What is cosine 130 degrees? Is it positive or negative? Negative. So this is positive, this is positive. This guy can be positive or negative. So the work done can be positive, 0, or negative. Yeah. When do you ever do negative work in your life? Do you ever do negative work?
That being if something was doing work to you.
No. So every time you're driving a car and you apply brakes, you're applying a force in that direction. This is 180 degrees. Cosine 180 is, so the work done is force times S times cosine 180, which is minus force times S. Okay, so every time you do negative work on an object, you're removing energy from the object. So when you want to stop a car, you're doing negative work on the car. Okay, so that kinetic energy of motion of the car, what happened to that? That all turned into heat. Okay, so in our life, we do positive works. Sometimes we do zero work, and other times we do negative works. Okay, so here are situations, and again, these formulas are applicable for straight line motion. We'll generalize this, and when the force is constant. Okay. So here was the initial position of the object. Here's the final position of the object, and as the object moved, this force was constant. Okay. If the angle between the force and the displacement is acute, in this situation you've done positive work. If the force and the displacement, the angle between the force and the displacement is obtuse, you've done negative work. Okay? And if the force and the displacement are perpendicular to each other, you've done zero work. Okay, so this diagram shows you all three cases. Okay. Again, so this formula is for a constant force, and the displacement is a straight line displacement. Okay. All right, so now we'll make the situation complicated one step at a time. Okay. Now we will vary the force. Okay, so we'll still move along a straight line, but we're going to change the force. Okay. So let me do a diagram. So we're going to move the object from here to there, and we're going to change the force. How are we going to change the force? Here's how the force is going to be pointing. Okay. So you see I'm changing the magnitude and direction of the force. Okay. Well, you're not afraid of this anymore. You've learned calculus. So what do? You know how to calculate the work done when the force is constant and the displacement is straight. So if the force is changing, all you do is you break it up into little segments of displacement, and in those little segments, the force is constant. How big are those segments? As small as you want them. Okay. Okay, so even if it's a fast changing force, you just break it up into smaller and smaller segments. Okay. What was the work done in a small segment? It was the component of the force along the displacement times the displacement. Okay. And we'll call it I. I labels the displacement. Okay. So it's this x component of the force times delta xi. Okay, so x component of the force times the displacement for that segment, and if the force is changing rapidly, you just make the segment smaller and smaller. So the work done is the x component of the force divided by that. Okay, so we'll call this the x component of the force fx. So it's a function of x. Okay. So this is plotting the x component of the force as the object is moving in a straight line. Okay. So the x component of the force is that. And so the work done during this small displacement is this. And then you add up all of that. And that's the integral of that function. Yeah. I is the ith segment. Yeah. I guess I need to fix those subscripts. Okay. All right, so what did we learn? Okay, so we started off with, we gave you the formula for a constant force along a straight line. Now we're still having the object move in a straight line, but what did we do? We changed the force. So no big deal, we just broke it up into little segments where the force was constant and just added up all those work done. Okay? And the work done in each segment was the x component of the force, which is what we call this. Okay, so this is the x component of the force at location x. Okay? Times dx, that's the work done in this small segment. And then an integral is just adding up all those little pieces. Yep. Mm-hmm.
This is a force that varies over distance?
Yep.
Not, the time doesn't matter.
Well, it's you're at different locations at different times, so it's a
Okay.
yeah. So if you want,
But like the x-axis.
it's a composite function. Okay, but we're
Yeah.
all right. So, but we're just going to give you the x component as a function of position and then do that integral. So here is an interpretation of this area. Okay, so you saw that when force is plotted as a function of position, the area under this curve is work. Okay, what are the units of this area? Area is length times width. Width is in meters. Length is in newtons. Newton meters, that's joules. Yep.
So you wrote dW, do you mean you're taking the derivative of work there?
This means infinitesimal amount of work. All right, so this is a progression. So we gave you the work done when the force was constant and the object was moving in a straight line. Then what did we do? We progressed to a varying force, but you're still moving in a straight line. And the work done was the component of the force along the displacement integrated over that. What is the last change you want to make? What is the last thing that you can change? I'm sorry? And not being a straight line. There you go. All right. What if it's not a straight line? What is the trick you would do? Break this path into little paths, which are straight lines. That's calculus, you know. All right. And do you know how to calculate the work done along a straight line? You do. All right. We'll call this segment dr. Okay. The work done on that segment is f dot dr. And then you add up the work done in all the segments. What does adding up mean? What is the other name for adding a whole? Huh?
A sum.
Yeah, that's an integral. Okay. And so here's the line integral. Okay. All right, so here we go. So for a general 3D trajectory, okay, for an object moving like that, and you're applying a varying force, the work done on this object in going from A to B is equal to the work done in this segment There's the work done on that segment, the small infinitesimal amount of work done in that segment. Okay? And then you add up all the little works done. Okay? So that's a line integral, and you learn how to do line integrals in Calc 3. Okay? For now, we'll just mention it. All right. We will do integrals in very simple cases. We won't do this general 3D case. Okay. All right, but so what have you learned? You learned how to do work when the force was constant and you were moving in a straight line. Then you learned how to do work when the force was varying but you were moving in a straight line. And then lastly, you learned how to calculate work when the force was varying and you were not moving in a straight line. Okay? So now you're experts at that. Okay? So now let's calculate some situations, some cases. Okay, so here's a here's a device that you have to become familiar with. If you're an engineer, you'll deal with springs all the rest of your lives. Okay, and in fact, this thing is so important that we have a separate chapter for this, chapter 15 or something like that. Okay. Here's what a spring will do, an ideal spring. Okay, so let's say you attach a mass to this spring, and if you pull the mass to this side, what the spring does is it pulls back on the mass. Okay, so this is the unstretched position of the spring. That is the equilibrium position. So if you pull the mass here, the mass gets pulled back. If you compress the mass, what the spring does is it pushes in that direction. Okay, so this is the equilibrium position, and if you disturb the object from the equilibrium position, the spring exerts a restoring force. Okay, it's bringing you back to your original equilibrium position. Okay, some of you guys did the lab on Monday about this. I mean, a sort of a similar lab. Okay, so the force on the object is the displacement minus kx. Okay. If x is positive, the force is in the negative direction. If x is negative, the force is in the positive direction. If x is negative, the force ends up being in the positive direction. Okay? This guy is called the spring constant. K is the spring constant. And that tells you how stiff the spring is. Bigger K is, stiffer the spring is, the harder for a given displacement, the harder the spring pulls back. Yeah. This is known as Hooke's law. Mr. Hooke discovered this. Okay. And a lot of materials behave this way. This is called elastic behavior. Okay, so for small displacement, the restoring force is proportional to the deformation. Okay. So for instance, when you bang this table, the table deforms, and the restoring force is proportional to the deformation. Okay? When you pull on a guitar string, okay, you change the shape of the string, and the restoring forces are proportional to the displacement. Okay? You jump and land on the ground, your bones deform, and the restoring force is proportional to the deformation. Okay? So a lot of things behave in an elastic manner. All right, so here's a force. Here's a force in the force has this is the component of the force along the displacement. Okay, so it's like this guy. Okay, the x component of the force, which is varying with position. Okay, so if the mass is here, the force is minus kx, and so on. Okay, so we'll do an integral. We'll calculate how much work the spring does when the mass moves from one position to another. All right, so we'll calculate the work done by the spring when the mass moves from this initial position to that final position. So here is the force that the spring applies, and we'll do an integral over x. Okay. And the integral of x is x squared by 2. K is a constant, so it's so let me do this. The integral of minus k is a constant. X squared by 2, and then you apply the limits. Okay. And there's the answer. All right, so let me point out something neat about this. So here was the equilibrium position. Okay. And let's say I move the object from x initial to x final. Okay, how much work did the spring do? It did 1/2 x final, kx final square minus negative of this. Okay. Now, how did we get from here to there? So let's see. Let's say we got from there to here like that. How much work was done? This much. Let's say we got from here there. How much work was done? Same amount. We got from here to there like that. Same amount. Okay, the work done was independent of the path taken. All right, so in fact, next time, you don't even have to do this integral when you're calculating the work done by the spring. The work done by the spring is just this guy. See, this is a scalar valued function. The value of that function at the final location minus the value of that function at the initial location. Okay, this function is called a potential energy function, and we'll talk about this, I don't know, maybe next chapter or something like that. A whole chapter to just that. So there are forces. These are called special forces. And to calculate the work done by them, all you have to do is take the negative of the potential energy function at the final point minus the potential energy function at the initial point. Okay. And so the thing is, you don't have to do the integral. And we like simplicity in life. Anything that simplifies our life, we're happy with that. Okay? So these are special forces. These are called conservative forces. And you will learn only the 3 conservative forces that you'll study are spring forces, gravity, and electrostatic. And we'll learn about these over several chapters. Okay. All right, so the work done by that force is negative of the potential energy function. Okay, so you saw how to calculate the work done for a 3D trajectory. It's a line integral. And you'll learn about line integrals in Calc 3. Okay, so here's work energy theorem. Okay, so when you do work on an object, you're changing the energy of the object. Okay, if you do positive work, you're increasing the energy of the object on which you do work. If you're doing negative work, you are decreasing the energy of the object. If you do zero work, What are you doing? You're not changing the energy of the object. Okay? All right, so we'll show this theorem to you. So we'll look at a very simple case. Here's a force applied to this object, and there are two other forces, the force of gravity and the normal force. This guy is sitting on a frictionless surface, so the net force on this guy is this force cancel that, so the net force on this guy is just the applied force. Okay? And if you apply this guy will accelerate, and so if he was at rest, he'll accelerate and he'll gain a final velocity. So his kinetic energy will increase. And what we're going to show is his increase in kinetic energy is equal to the work done by this force. And that's the work energy theorem. Okay? So remember, by doing work on an object, you're changing the energy of the object. Okay? Yeah, so that's what this calculation shows you. Okay, so how much work was done? The work done by the net force. The net force happens to be this force. Is force times this dx, this integral. Okay. Now this is constant. So, well, again, it doesn't have to be constant, but so the force is the mass times acceleration of this object, mass times acceleration of the object, dx. And let's say the velocity of this object, so the velocity of that object is position dependent, which is time dependent. Okay? So m dv by d. So dv by dt, you can use the chain rule, is so dv by dt is equal to dv by dx times dx by dt. Okay? So using the chain rule, and that's what this is. Dx by dt is the velocity of the object, and so dv by dx, dx by dt, dx. So this is equal to dx by dt is the velocity of the object. So you have the velocity of the object, dv by dx times dx. And this is dv. That's the change in the velocity when the object moved at distance dx. Okay? So work is mv dv. So essentially what we've done is, see, this integral over d was over dx, and what is this integral over? Dv. So we made a change of variables. That's what it amounts to. And this is an integral of v dv. It's like x dx. The integral is v square. And so this integral is m v square by 2. And the limits are v initial and v final. Okay, so the work done by the net force showed up as change in kinetic energy. And that's the work energy theorem. Okay. So if the work done is positive, the kinetic energy will increase. If the work done is 0, the kinetic energy will not change. If the work done is negative, the kinetic energy will decrease. Okay? The final kinetic energy will be less than the initial kinetic energy. And that's what happens when you apply brakes on your car. Your final kinetic energy is smaller than your initial kinetic energy. Okay? And you've done negative work. All right. So there's the work energy theorem. The net work done is the work done by all the forces acting on the object. The sum of work done by all the forces acting on that object, and that shows up as change in kinetic energy. Power is the rate at which you're doing work. So this is how much work you've done, and that's the amount of time you took to do that work. So if you do the work faster, your power is greater. Okay? So power is the rate at which work is done. Units are joules over seconds. Joules over seconds are called a watt, after Mr. Watt. And so back in the day, it turns out that 745 watts, 746 watts is 1 horsepower. Okay, so that's the rate at which an average horse could do work, and it could do work for 8 hours. Okay, so that's horsepower. Okay, oftentimes we apply a force and the object is moving, and the force applied is constant. So when you're driving at a constant velocity on the highway, okay, your engine is applying a constant force. You can think of it that way. And so power is rate at which work is done, and if you take the time derivative of that, force is constant, that comes out. And so dr by dt is your velocity. Dr by dt is your velocity. So the rate at which you're doing work when the force is constant is force dotted with your velocity. Okay, so that's the rate at which you're doing work. So here's an interesting diagram. Okay, so this says maximum power output from humans for various time periods. Okay, you see that. So if you want to work an 8-hour day, you can work at a rate of 75 watts, which is 1/10 of a horsepower. So you could work in the fields, or you could employ a horse, and that horse could do 10 times your work. So, okay, a horse could work at the rate of 1 horsepower for 8 hours. Okay. If you wanted to work at the rate of 1 horsepower, at the rate of 1 horse, you'd last about 60 seconds. Okay, here's the interesting thing about this guy, about this thing. So, an average human being, if you work at the rate of 1/3 of a horse, you could last about 30 minutes. This guy rode this human-powered bicycle across the English Channel, and he was pedaling for 3 hours. Okay. Now you might say that he had the motivation because if he quit pedaling, the sharks would get him. But he was an athlete. Okay. Well, I mean, so that's what elite athletes can do. Okay, here are some numbers that you need to be familiar with. Okay, Hoover Dam is a large power plant. A large power plant is, the approximate power is 1 billion watts. Okay, so 1.5 billion watts or whatever. Okay, what you can do with this thing is run about 1 million homes in the US. Elsewhere you could run more homes, but that's what you can do. So a large power plant is about 1 billion watts. And these days, if you get this energy from a wind farm or a solar power plant, this costs you about $3 to $5 billion. And of course, solar and wind is the cheapest form of energy. Okay. So that's what it costs. A nuclear power plant, unfortunately, costs a little more, but anyway, that's, I guess, so you want to know that. The refrigerator is one of the largest power consuming device in your house. It's 600 watts. Your energy consumption to run your system, your body, you need 100 joules per second. Okay, so you're like a 100-watt bulb. Look at this. Your brain is using 20% of that energy. Okay. It has to coordinate all the systems that are at work. You know. So here's the amazing thing about the brain. Okay. How much power is this thing using? This is a 100-watt device, same as your body. What is the most powerful computer in the world? Your brain is the most powerful computer in the brain. in the world. Okay? There's one attached to every shoulder. This device is as powerful as maybe 100 million of these, and it's using 1/5 the power of that. All right. A kilowatt hour. Okay. So remember, power was work or energy, work divided by time, or energy used divided by time. Okay. So energy is power times time. Okay. Watt is a unit of power, so kilowatt is a unit of power, and hour is a unit of time. So kilowatt hour is a unit of energy. Okay, and so let's see what that is. A kilowatt is 1,000 watts, and 1 hour is 3,600 seconds. So 1 kilowatt hour is roughly 4 million joules. Okay, this is the unit of energy by which your electric company charges you. Okay, so you can go look at your electric bill, and this costs you about 12 cents. Okay. It costs them about 4 to 5 cents to produce. Okay. All right, there's another topic I want to talk about.